In the last few videos, we've been discussing waves and developed our wave model for how we describe them. And it boils down to describing the displacement of some medium as a function of position and time as being equal to a sine kx minus omega t plus phi naught, right? And what this is essentially we've got an amplitude, which is the maximum displacement of our medium. We've got this whole argument of the sine function is what we call the phase of the wave. And it has three different parts to it. This kx, well, the k is what we call the wave number or wave vector. Uh, vector. Which kind of captures the periodicity in space of the wave. That's 2 pi over the wavelength. This omega is our angular frequency or angular velocity. And it captures the periodicity in time. It's 2 pi over the period. And this last term is what we call the phase constant. It is the constant term in the phase of our wave. And it allows us to sort of describe arbitrary initial conditions. If we set t to 0 and all that, this will shift the sine function left or right so that it's describing the situation appropriately. We've discussed how to different ways of visualizing these waves, right? If we were to plot, so the typical example we've been using is a wave on a string. So if I want to plot the displacement of that medium, the string, say, as a function of position, this function would it'd be sinusoidal. It would look something like this. And we know, so this is what we call a snapshot graph. You pick a single instant in time and plot the displacement of the medium over all space. And we can identify the wavelength as what we're familiar with, the distance between two crests or two equivalent points on the wave. We can see this sine wave is shifted by some oops, do that the wrong way. The sine waves normally a sine looks something like this, where it starts at 0. So this wave has been shifted by an amount equal to the phase constant, right? So that's where the phase constant is. If we were looking at t equals 0, say, this wave, this sine wave wouldn't be strictly a sine wave. It would be some shifted sine wave shifted by that phase constant phi. We also know how to plot this in what we call a history graph, which is the displacement as a function of time, right? We pick a single instant, a single location in our medium and plot the displacement as a function of time. And again, for these types of waves, we're going to get something that looks sinusoidal, something like that. We can identify the periodicity in time as the period of that wave. And again, this is all captured in the angular frequency. Now, this was in one dimension. If we go into bigger dimensions, if we think of like a speaker in a room, well, that speaker would sit at some point and it would emit waves in all directions. So it would look something like this. We can visualize the waves by just drawing lines that represent the wave fronts or essentially the crests of that wave. And the spacing between those is equal to the wavelength. These are supposed to be concentric circles, evenly spaced. And we can visualize things that way. Other ways that we can describe the wave or essential properties to it, one big one is that Waves are disturbances traveling through mediums at a constant speed. So that wave speed, one of the ways we defined our wavelength was as the distance traveled by a disturbance in one period of motion, i.e., the wavelength was divided by that period of motion gives us our wave speed, right? The wavelength is the distance traveled by the disturbance, and the time it takes to travel that distance is one period, so it equals that. Or written another way, it is equal to lambda times the frequency of that wave. So this V equals lambda F is a really sort of fundamental wave property of our waves. And an interesting thing to note here is what sort of determines these properties? Well, the wave speed is determined by the medium, right? If you think of sound in air, the speed that sound travels at is determined by the properties of the air. What's the pressure, the temperature, sort of thing. So the wave speed's determined by the medium, whereas the frequency, well, that's determined by the source of the wave, right? If you think about the frequency of a sound wave, when we were drawing this two-dimensional sort of visualization of the wave, we were thinking about a speaker in a room playing some sound. Well, if that speaker is oscillating back and forth at a frequency that's, say, a C note, that speaker, the frequency of that speaker determines the frequency of the wave. So you can look at things like this and different situations and sort of keep that in mind to determine the properties of the wave. Anyway, this is a brief little recap of the wave model that we've put together, and it can describe essentially all the types of waves we're going to think about: sound waves, light waves, waves on a string. It can even describe, you can use it to model like traffic waves. If you've ever seen like in a traffic jam, the compressions and all that between cars can be described as a wave. Anyway, what we're going to do today is we're going to move on and we're going to start to describe different properties and things you may notice with waves. Specifically, we're going to look at the Doppler effect. The Doppler effect is sort of a property or a thing that happens with waves when you have objects that are moving, that are creating these waves. The most familiar example you're probably familiar with is cars driving by, and the frequency that you perceive that sound of the car or the object that's moving changes based on how it's moving. So it's this sort of example here. So you notice the pitch of that horn was really high pitched when the car was driving towards you, and then changed to a lower tone when it passed you. You get that sort of when the car passes you. If you've ever watched racing, car racing or that, you're probably very familiar with that sound. Anyway, that's called the Doppler effect, and you get this Doppler shift in the frequency of the wave you're hearing, and it's used. You see it not only with sound and all that, but all types of waves. And astronomers actually need to use this. They use it to determine how fast planets and stars are moving, because if a star is moving away from you, its frequency is Doppler shifted. If it's moving towards you, it's Doppler shifted. The relative speeds of the observer and the source determine how those frequencies are measured. So how can we explain that shift in frequency? Well, to do this, we're going to just sort of consider the source of some sound. And let's say we're over here and we're the observer, right? So there's the observer, there's the source. And let's have this source moving towards the observer at some speed v source. Now, the way I like to think about this, and that is, let's think about what, let's think about sound waves, and let's think about the source as essentially continuously disturbing the medium, the air in it. But just consider it as like that source is throwing crests of waves at you, right? So at t equals 0, the source is here, and it throws a crest, right? So we're going to use these just lines to indicate where the crests are. And consider 3 periods later. So the time is 3 periods later. Well, we can ask, well, how far is that first crest gone? Well, it's going to have moved some distance to the right, and it's going to be sitting here at, we'll call it x1, the position of the first crest. And that distance is just the speed of sound times how long it's been moving, 3 periods, right? Now, if we think of 1 period later, well, this source will have moved to some distance. It'll now be here, where it's moved the speed of the source times 1 period distance away. And that's where it's going to throw its second crest, right? And it's going to then, that crest for the next 2 periods will have moved some distance like this and be sitting at x2, where it's moved the speed of sound times those remaining 2 periods, right? And if we think about what this is, the first one went some just resting wavelength, 3 of those in 3 periods. This one, the second crest moved some amount that the source moved for the first period, and then sort of 2 wavelengths since then. And it keeps going like this. At a period later, the object will have moved, the source rather will have moved the speed of the source times 2 periods, and the crest for the last period will have moved to some position x3, which is the speed of sound times the period. And it's going to go like that. But if we are over here and we're the observer, what do we see? Well, here's x1. Here are the positions of the crest. We observe this wavelength, lambda, right? Which is going to be different from this wavelength. It's going to be sort of compressed a bit. So let's ask ourselves, what wavelength do we observe? Right? And to do that, well, our wavelength is just going to be the distance between those 2 crests. It's going to be x1 minus x2. Well, what is x1? Well, it's just how far that crest moved in those 3 periods. So that's the speed of sound times 3t, right? And what's x2? Well, x2 is how far the observer moved in the first period. So that's the speed of how far the source moved. So that's the speed of the source times 1 period. And then plus how far the crest moved after the source threw it, which is just the speed of sound times 2 periods, right? So if we get this, and we do this math, we get 3t times v minus 2t times v. That gives us the speed of sound times 1 period minus the speed of the source times 1 period. Or if we do some factoring, we have the period times the difference between the speed of sound and the speed of the source. It gives us that wavelength, right? So we see that the wavelength is going to change. But what we observe, what we're familiar with the Doppler effect is not a change in a wavelength. We hear a frequency, right? So what frequency do we hear is the question we really want to get at, right? So, well, we know one of our descriptions, the way we describe waves is we have the wave speed is equal to the wavelength times the frequency, right? But we've just determined what this sort of wavelength is for this sound wave with the moving source. So this tells us that our frequency is the speed of sound divided by that wavelength, or v divided by the period times v minus vs, right? This is essentially what the Doppler effect is. We can clean it up a bit by doing some algebra, right? The frequency is going to be equal to the speed of sound time divided by the period. We can factor out a speed of sound down there, and this becomes 1 minus the ratio of the speed of sound to the speed of the source. These velocities then cancel. And also 1 over the period is just the frequency of that sound if we're standing still. So this frequency, when the source is moving towards us, is equal to the frequency when it's at rest divided by 1 minus the ratio of the speed of sound to the speed of the source, right? And this tells us, this is what we've just derived is what the frequency we would hear something at should a source of that sound be moving towards us. Now, if it was moving away, the only thing that really changes here is this would be going the other way and we would have to subtract it. So we do all the same math, except for this comes out as a plus here. So this is for the source moving, right? And that's what we get. That's the Doppler shift for a moving source. Turns out it's a little different if we have the object moving, right? And the reason is this: if we have the source of sound staying stationary, the wavelength is the same. The distance between those crests in space is always just going to be that wavelength of that sound. But if we, the observer, are moving, towards it, we're gonna how frequently we run into these is going to be different. Or if we move away, how frequent we see those crests is going to be different as well, and that leads to a slightly different equation. What you end up with that case is if the object's moving, you end up with the frequency, if it's moving towards you, is equal to 1 plus the ratio of the velocity of the observer to the velocity of sound times the rest frequency. And if it's moving away from you, it's just minus. So these are the way we can calculate Doppler effects. One for the source of the sound moving, one for the object is moving. In both cases, if the observer and the source are moving towards each other, that frequency goes up, right? In the source moving case, we have 1 minus some number less than 1, some positive number less than 1. So that's going to make the denominator smaller, and this frequency goes up. If you're moving away, the opposite happens and that frequency goes down. In the object moving case, if you're moving towards the source, this is going to be a plus. That's going to get a bit bigger and the frequency is going to go up. If you're moving away, it's a minus and it gets down. But that's mathematically how we describe the Doppler effect. Visually, it looks like this. If we have, two observers, we'll say Pablo here on the left, Nancy on the right, and we have some source of a wave that's moving to the right at some speed v source, as we discussed in our derivation, if it's moving towards you, so if you're Nancy and that source is moving towards you, we see these wavelengths have gotten shorter, and that leads to an increased frequency. Whereas if you're Pablo observing on this side, where the source is moving away from you, those wavelengths have gotten longer, and that leads to a decreased frequency. Anyway, hopefully you're all familiar with this, like in practice. Like you've heard, cars have driven by you, and you maybe have noticed the slight change in pitch of the engine as it's approaching you versus going away from you. If you have questions about this, please email me, bring them up in our synchronous sessions. We'll do a few examples and such. Hopefully it's all starting to make sense though. I will see you in our synchronous sessions.